Okay, welcome to the Objective-C open office hours for January 3rd, 2013. I'm going to be here. My name is Nelson, and so will Nina.
Hello.
Hey, so Jason will not be joining us today for this class. Instead, what we're going to be doing is we're going to be talking about some of the concepts that people may be having trouble understanding. So we're going to be talking about things like pointers and memory management, just overviewing all of that fun stuff. So it's the 3rd, not the 13th? I don't know what day it is. I don't pay attention to days. Who pays attention to days? Okay, so we have gone over what pointers are, and a pointer is basically a variable such as an integer. That has a little star next to it. And we have a type. Now, the funny thing about pointers that people have a very difficult time understanding is that pointers are just variables. I mean, just like an int num equals 10, this is a variable, and so is this. They're both variables. They both have types, and they both have identifiers. They're both local variables. And the funny thing about these is if we put these in a stack frame, like if we do something like int main, so now these are variables that are local to the main function. We have now created a stack frame with two local variables on it. One's an int and one's an int pointer. So what I'm going to do here is I'm going to write out some code. I'm going to initialize pointer. Instead of terminating that line right there, I'm going to delete that little terminator. I'm going to say equals address of, using the ampersand, or whatever that squiggly mark is. It's supposed to be an ampersand, num. So let's go take a look at the stack of main, because we talked about how we have different stack frames. So here is our main. See, I'm writing at an angle here, and it's really strange. Let me reorient my
Stop it.
tablet here. And
Stop that.
I'm knocking. Everything is just. See, whenever Apple products get involved, things like this start to happen.
Uh-oh.
Oh, did I say that out loud?
Uh-huh.
Alrighty, so.
You might hurt somebody's Apple feelings.
But Applejack, you're the best Apple thing of them all. Anyway, so we have our main stack frame. What's in it? Well, we have two local variables. And what I'm going to do is I'm going to draw a nice little diagram of our main stack frame, or a nice little table of our main stack frame. We have our variable. And every variable has a type, a size, an address, and a value. So is everybody good so far? We have our main stack frame, and our main stack frame contains local variables. And every local variable, no matter what it is, always has a name, an identifier, a type, a size, an address, and a value. So what's our num? Well, if I were to fill out num, it would look like this. The variable would be called num. The type would be of int. The size, I'm just going to say 4 bytes. Now, the size of primitive types can change depending on your compiler architecture, but I'm just going with 4 bytes, which is pretty standard across most platforms and compilers. The address, I'm going to make up an address here. I'm going to say 0x04. That's going to be my address for this variable. I'm just making that up. And its value is set to 10. Okay, so help me out here, guys. Let's go ahead and fill out the. Does everybody understand the table here? What the table is representing? Our table represents the different attributes of, in this case, the num variable. Is everybody good so far? All right. People who are particularly new to pointers, I want you to help me out here. How should I fill out the next column? The next column is going to represent the pointer variable, the variable named PTR. What should I put in the first column here? Anyone? Yep, PTR. What should I put in the next column here? Terry Norton almost got it right. MMO Dust, you should be more specific. Yep, Terry Norton got it right. It's an int pointer. So the way we represent an int pointer in most languages that support pointers is int asterisk. Now, what's its size? Now, this might be a little bit of a tricky one for people, but the size of a pointer is always constant. So even if I had a double pointer, even though a double might take up 8 bytes of memory, a double pointer is going to take up the same amount of space as an int pointer, because all a pointer has to do is store a reference to a location on either the stack or the heap, a memory address. And the size of a memory address is determined entirely by the architecture that you're compiling against. If you are compiling against a 32-bit architecture, that means your CPU is capable of understanding memory addresses that are up to 32 bits wide, or 4 bytes wide. If you're compiling against a 64-bit architecture, that means your pointers must be 8 bytes or 64 bits wide. That's why a 64-bit system can actually access more memory than a 32-bit system, because a 64-bit system has bigger pointers. Now we're going to pretend that we're working against a 32-bit operating system, and we're compiling with 32-bit code. Given that constraint, what should go in the third column? Right. The size of our pointer is 4. It has nothing to do with the fact that we're pointing to an int. That's not why it's 4. It's 4 because we have a pointer. And because in our imaginary operating system we're compiling against 32-bit CPUs, all pointers will be 4 bytes wide. Now its address. I'm going to just pretend that this pointer is snuggled right up against this num, and I'm going to give it the address of 0x08. So it appears immediately after on the stack as num. But here's where things get tricky. What is the pointer's value? What is contained inside of not the data that the pointer is pointing to, but what is contained in this memory address? Right. The thing that is contained in this memory address is 0x04. The value of the pointer is going to be the address of this thing that it's pointing to. So, if I were to do something like this, if I were to say printf, I'm just going to completely ignore format specifiers right now, just for sake of simplicity. So I'm going to say print dereference PTR. Then I'm going to say printf PTR. Can anyone tell me what the value of this, or the output of this program will be? What will the output be of these two print statements? Ray Lewis. Anyone else? Anyone? Can anybody guess? Come on, give another guess. Let's go. Yep, Rowdy Bull, got it. The output of this program is going to be 10 for this print, and it's going to be 0x04 for this print. And here's why. When you dereference a pointer using this syntax, what it's going to do is it's going to look up the value of the pointer, right? That's the first step. But once it has the value of the pointer, it dereferences that value by finding out what's contained at the address that the pointer is pointing at. So 0x04 is going to jump into whatever variable is stored at 0x04, which in this case is num. Then it's going to grab the value that's contained at that address. This is a process known as dereferencing. We prefixed the pointer with a star, and so we've told the compiler we want to dereference this pointer. So to dereference it, we first look up what value is physically stored in the pointer's memory. Because the pointer does consume memory. The pointer is just a normal, straight-up variable that is on the stack just like every other variable. So it has a value. But its value is a special kind of value, which is a memory address. And when we dereference the pointer, we get its special value, and we search, or we use that special value to find another value. And that's how this is called indirection, or dereferencing, because we're dereferencing this address, searching for the variable that's stored at this address, and grabbing its value out. The second one, we're just printing pointer. We're not dereferencing pointer. We're not doing anything special with it. We're just printing it. So what's going to happen? Well, pointer, straight up, is a value. It's just a normal variable, and it's going to be printed as if it were a normal variable. So that's why we get 10 followed by the address. You follow along, Nina?
Yes.
Okay, so are there any more questions about pointers? So this was just a basic recap of what pointers are.
Yay, pointers.
How's everyone feeling? Right. The star after a type defines that that type is a pointer type. So when I say int star, I am basically annotating the int type and saying, I don't want an int, I want an int pointer by adding the star after the int. However, adding a star before an identifier is known as the dereferencing operator. The dereferencing operator will do what I described earlier. It'll look up the value of the pointer, go to that memory address of where the pointer is pointing to, and yank the value out of that.
Rowdy says it throws him off when he sees them in methods.
Right, because you can pass pointers as if they were just normal variables. I can write a method called int. My wireless dongle isn't dongling very well. We could write a method like int foo that takes in an int pointer. What we're doing is this is the type of the parameter, int pointer. We're not dereferencing pointer. Now, we certainly could dereference pointer inside of info. I can say star ptr equals 20 and then return if I wanted to. In this case, this method should be returning void, not int. But what this shows is the two contexts that pointers are available on. This context means a pointer type. This context means a dereference. This is the same explanation for the pointer before and after. It doesn't matter which order the asterisk appears in. Some people are horrible, horrible, horrible people, and they like doing things like this. And those people should have their programming privileges revoked. However, this code right here is equivalent to this code right here. Remember, C is a white space insensitive language, meaning that if the white space is here or the white space is here, it doesn't matter. It's going to execute as the same code. So the method is expecting a memory address. Yes, the method requires that you pass in not an integer. It doesn't want an integer, but it wants a memory address of an integer. I like Nelson because he's so tolerant. I am so tolerant, aren't I? No, I have opinions, and there's a reason why I really despise the fact that some people like to place the star next to the identifier instead of next to the type, because logically the star is associated not with the identifier, it's associated with the type. What you're doing is you're saying, I want an integer pointer. You're not saying, I want an integer pause pointer of a called pointer. You're saying, I want an integer pointer pause pointer. And you're working with object and primitive types the same. Yes. Pointers to objects and pointers to primitives work exactly the same in Objective-C. They're the same thing. So whenever you see a method in Objective-C that's accepting an object pointer, what it's asking for is the memory address of an object, not an actual object.
Hey, should I text it to her or write it?
And num can use the ampersand to give its memory address. Right. The ampersand is called the address of operator. So if I take a normal variable and do print address of num, this operator right here is called the address of, and will return the address of wherever num is resident inside of memory. So that's how we can take a normal variable and turn it into a pointer by using the address of. So there's three symbols that you need to be aware of when working with pointers. There are three very important symbols, and unfortunately one of the symbols is the same thing. We have the type annotation, which is a type followed by a star. This means pointer type. We have the star followed by a variable. This means dereference. Then we have the ampersand next to a variable. This means address of. And Ray Lewis got right. Thus, int pointer equals address of num. Because the address of actually converts the type of the variable into the corresponding pointer type. So if we want to think of these expressions in terms of the types they return, double bleh and float whoa. If I did address of bleh, the type of this expression is double pointer. If I did address of whoa, the type of this expression is float pointer. It just changes the type. Should it be dereference space var or dereference var? I would prefer there not to be a space here. I always dereference my variables by passing a asterisk immediately before the identifier. And again, C and Objective-C are white space insensitive, meaning you can place as many bits of white space between the star and the variable, but I would highly recommend sticking with placing the star immediately next to the variable for dereferencing. But these are the three symbols or two of them are the same, but you know what I mean, that are very important for working with pointers. Do you ever use ampersand after anything? Typically, no. But I do want to quickly point out something that might be confusing for some people. In C++, not in C or in Objective-C, but in C++, remember that C++ is a superset of C, just like Objective-C is a superset of C? That means in C++ you have all of this stuff. All this stuff is still completely valid, but you have one more thing. And that's called, if you do a type followed by an ampersand, this is called a reference type. And a reference type is very similar to a pointer, but it has more limitations. So I just want to point this out. Just if you guys are reading C++ code and you see this is C++ only. But these three are shared. So these three are shared between C, C++, and Objective-C. Okay. Any more questions about pointers? So just to reiterate, all of this stuff can be applied to both objects and primitives. And we'll see examples of working with objects here in a moment once we start talking about releasing and retaining and allocking and deallocating. All right, if there are no more questions about what I just talked about, I do want to point out one more I made a programming joke. I do want to point out one more thing about pointers that is very confusing, and I won't be talking about it, but I do want people to be aware of this concept because you will see it in certain cases. You may even want to use it at some point, and I just want to point it out because, at least for me personally, having this particular bit of knowledge does help solidify pointers to an extent. So I'm going to go, no. Let me go ahead and move you over here. And then I'm going to erase you. And Nina talks loud sometimes. Then I'm going to take you, move you down here. Delete all you. Okay, are you guys ready to have your minds blown? I bet some of you know already where I'm going to go with this. My tablet just died. What? No, stop that. Come back. There you go. Okay. So you guys ready to have your minds blown?
I had to step away, Nelson. I'm sorry, I'm back.
That's okay. Can anybody tell me what this is?
What is it? Where a pointer lives, Ray says.
I'm not sure I understand what you mean by that.
Pointer to an int pointer.
Yep.
That's MMO Dust and Terry.
It is called a pointer pointer.
Double pointer? A pointer pointer?
A pointer pointer.
All right.
That's why I called it PTR PTR.
Gotcha.
Let's take a look at what a pointer looks like on our stack. So PTR is of type int pointer. What's its size? 4. What's its address? Zero x 16? Well, no, I would put it at 0x12. What's its value? Yep. Its value is the address of 0x08. What we have here is a pointer to a pointer. And what a pointer to a pointer does is it's, well, a pointer to a pointer. It's done with this syntax, double pointer, and it has an address and a size just like every other variable, but its value is not a pointer to a variable. Its value is a pointer to a pointer. So if I wanted to dereference my pointer, if I did PTR, and then I did dereference PTR, and then I did, hold on. And then I did dereference PTR. Now pretend that I have all of these three things in printfs. What is the output of each one of these lines of code? MMO Dust, you're close. Yep, Ray Lewis got it. So the PTR, if you do not dereference it, it'll just print its value. And its value, while the value is a special thing called an address, it really just is a number. So we can treat it like a number. And what do we get back? 0x08. Now what happens if we dereference pointer? If we dereference pointer, we look at the address that pointer is pointing at, and we look it up. And what do we get? We get the address of pointer. Then what's the next step? Well, we find out what the value is at that address. And what's the value? The value is 0x04. The last thing we do is we dereference, but then we dereference what we dereferenced, which means that we go from 0x04, we look up that address, which is an integer right here, which if you remember is our num variable, and then we look at the value of num, which is 10, and we get 10. So one dereference does not go to the bottom of the stack. No, the dereference is local. The order of operations looks like this. The first dereference happens, and then the second dereference happens. They're two completely independent operators. How deep can this go? Well, how many asterisks can you store on your hard drive in a text file? And there's your answer. I mean, basically, to sum up that answer, however deep you need to go. Compiler does not care, no. Why is this useful? Well, have I ever told you guys that that's my least favorite programming question ever? Why is this useful? The fact is, if you have a Turing-complete language and you understand if statements, loops, and dynamic memory allocation, and basic I/O, you can pretty much write any program you want. The whole idea of a programming language is to give you tools to make certain things easier. Pointers are not used very often. The reason I wanted to go over these today wasn't so that you guys would find a use for them. I just wanted to make it very, very clear that there's nothing magical or special about a pointer, and you can have a pointer to a pointer if you want by just simply adding an extra asterisk. Sabai, I wasn't saying don't ask questions like that. I guess I probably came off a little bit too strong in that case. No, certainly ask why things are useful. But I just wanted to point out that this one is a very hard thing to justify the use of. And it is because it's a very complex thing that isn't used very often. In fact, only one library I've ever used, DirectX, has required me to use pointers. And the only times I've ever used pointers in my own programs was really esoteric edge cases where I decided to write something for fun. So yeah, not particularly useful. And yeah, don't apologize for asking why this is useful. I'm just saying that in some things, especially pointers, it's very difficult to justify the use of, but it is something that I like people to know. And I hope that some people at least got a little bit better I hope I didn't confuse people more with the explanation of pointers. I just wanted to solidify the fact that pointers are just variables, they're just values, they're just addresses, just like everything else. There's nothing special or magical about pointers at all. They're just variables that are treated by the compiler a little bit differently. So pointer is the value, and dereference pointer is the value of a value, and dereference pointer is the value of the value of the value. Let's see if I get that. Pointer, this is the value of pointer. This is the value of where pointer is pointing at. This is the value of what is. This is the value of what. This is the value of what the value of pointer is pointing at. Did I say that right?
I don't know, did you?
I don't know if I said that right. But I'm pretty sure what Rowdy Bull said was right. Pointer is the value. Dereference pointer is the value, is the value of where pointer is pointing at. And dereference pointer is the value that... Nah, I'm not even going to do this anymore. You get what I'm saying, I hope. Are there any more questions? Because that's about it as far as a quick recap over pointers for people. I hope some people get a little bit more solid understanding of things, because now we're going to move on to memory management. Memory management and pointers are very similar concepts, and they pretty much need to go hand in hand. Because what we have in our program is we have these awesome stack frames. We've talked a lot about stack frames. So we have like int main. An int main is a stack frame, and inside of the stack frame it has variables. And then we might have a void foo, and void foo might have parameters that are pushed onto the stack, and it also might have variables that are pushed onto the stack too. And so stack is a very horrible looking line. The stack is a very nice little safe place for us to put things. But unfortunately, it's not as useful for solving certain types of problems. Particularly, the stack is static. This is static memory. And it's not static memory in the sense that it's never allocated. It is allocated, but it's allocated in a special way. The stack is allocated when your program is launched, and the size of the stack is determined at compile time. Void foo, this method, or function, contains parameters and variables. And the amount of parameters and the amount of variables it contains will never change once it's compiled. That means the compiler can say, okay, foo, let's give it 12 bytes. Every time foo is invoked, we'll allocate 12 bytes on the stack. Never more, never less. Stacks are static. So the stack will never change in size for an individual function call. However, we also have a place called the heap. The heap is dynamic. Do I have the right pen? Just feeling like my nib is worn a lot further down than it should be. I feel like I'm scratching into my tablet. Hope it doesn't break it. Anyway, so the heap is dynamic. The heap contains objects that can exist between method invocations. So for example, I can have a person object. Okay, that's just getting ridiculous. I'm going to plug my tablet in. Stupid wireless dongle doesn't seem to work on Mac. It works fine on my PC. You know, I thought Macs never broke. Somebody lied to me.
Deep.
Okay, now we're plugged in. We should be a lot smoother. Okay, so we might have an object called like person. And the great thing about allocating a person object on the heap is that this person can exist between invocations of methods. So for example, I'm gonna draw another stack over here. Let's ignore the first stack that I drew. We don't need him anymore. Go away. Draw another stack over here. So I have main. Now main may say something like person pointer equals, or person pointer person equals, and I'm going to use the new operator. The new operator is what you would see in C++ or C# or Java or Ruby or Python or basically every language that isn't Objective-C. And because of that, if I try to concentrate on both the diagramming out and doing something that I'm not comfortable with, I'll end up just screwing it up for everyone. So I'm going to use the new operator to instantiate my person. In Objective-C, this would be the Dialyc message. So I would say person equals new person. Well, what happens here? This is an expression. This expression is called an instantiation, and it results in an object being placed on the heap. What is this? Can anybody tell me what that is? It's a person pointer, exactly. Where is this variable stored? Right. This variable is stored on the stack. So if I looked at the stack frame of main, it'll look like this. I have a variable called person. He's of type person pointer. He has a size of 4, because we're assuming we're on 32-bit operating system. And he has a value of something. Now what's his value? Well, let's say that in the heap, this is at address 0xFA. Or let's just throw in some numbers instead of hex. 14. So person is on the heap. This object, this memory, is stored at 0x14, which means the value of our person pointer is now 0x14. So the pointer itself is on the stack. The thing that the pointer is pointing to, however, is on the heap. So that's a very important concept to remember, which means that if I had another method, or another function, sorry, I'm going to get that, I'm going to say the wrong one many times throughout this, so just bear with me. If I had another function called foo that took in a person pointer, called person, or how about PER, just to make things less confusing. And I invoked that function from within main. So if I did foo and I passed in person, and let's say inside of here I did print per name. So what's going on here? What gets copied into foo's stack frame? The address of the object, 0x14 specifically. Yep. So here's main stack frame. So this is main stack frame. Here's foo's stack frame. And foo's stack frame looks like this. There's a variable called per, is of type person pointer. He's 4 bytes wide, and his value is 0x14. That's because the value of this argument gets copied into the value of that parameter, which means that this per is still pointing to the same object on the heap. The pointer itself is passed by value. That's an important concept to understand. Technically, when you say pass by reference, you're not actually passing by reference, you're passing the reference by value. I'm telling foo that there is a person object somewhere. It could be on the heap, it could be on the stack, it could be anywhere in memory. But I am telling foo that there is a person somewhere, and I'm telling it where to look for that object. So then when I do a member access using this syntax, I'm telling it to dereference this per, which points to this object. So is everybody with me so far? And if you're not, seriously, speak up. Is the pointer dereference operator in Objective-C? I think it is. I thought Jason was going to go over that in the next class. I can't remember. Just a warning, I'm not an expert of Objective-C. If I was, I'd be writing the pseudocode in Objective-C. The arrow, what does that mean literally? It literally means dereference this object and return a member from the dereferenced object. So it says dereference per, which means find out where per is pointing and then get that object and then get its name property out of it. This is syntax that you will see very commonly in C++ and in C. I know for a fact that the syntax is valid in C when you're working with structs, but I can't say for certain if this syntax exists in Objective-C, and I'm terribly sorry. Yeah, it is a short way of writing it. An alternative to doing this would be something like dereference per, and then instead of using the arrow, you'd use a dot. So dereference per, and then grab his name variable out of it. Well, if it's in C, then it is, right? Well, yes. When I said I don't know if that operator is in Objective-C, what I mean is I don't know if that operator can be applied to classes that are written in Objective-C. Now, it certainly could. I know for a fact that operator will work when using C structs, but I just don't know if that operator translates into Objective-C classes. Either way, there are similar constructs in Objective-C that allow you to do the same thing. So the concept is the exact same. So ignore the actual syntax that I'm doing here. The concepts are what matters. And what I'm doing here is I'm saying dereference per, get it, retrieve it from the heap, and access his name. Okay, so I know this was just a quick overview of dynamic memory allocation and passing dynamic memory around. We haven't actually talked about dynamic memory management yet, and I do want to diagram that
Well,
up.
why not?
Well, because we've been leading up to that, and people have been continuously asking questions, so I assume that because people are asking questions, they're learning stuff, and if they're learning stuff...
They're learning stuff and things.
Yeah, stuff and things. So if they're learning stuff, then I'm fine doing whatever tonight.
Yay!
But I will be going to memory management here very shortly because all of the stuff that we just talked about is a prerequisite to understanding what we're going to be doing with the retain and release. But I'm out of coffee, and so I'm probably going to abuse my powers as teacher to put us all on break so I can grab coffee and a cigarette. So I will be right back. And we're back. So we reviewed pointers, and we also took a very, very quick and very shallow look at basic memory management. But memory management gets complicated. And like all complicated things, we can make it less complicated by understanding the rules. So there are a few very important rules in terms of memory management. The problem with the heap, the fundamental issue with the heap, can anybody tell me what the fundamental issue with the heap is compared to a stack? The problem with the heap. Every language has this problem, and every language has its own way of solving it. But there's always one problem with the heap compared to the stack, and Ray Lewis got right. Everything you allocate on the heap sticks around. Now, when you invoke a function, a stack frame gets allocated, and then when the function is over, the stack frame gets deallocated. All of that happens for you automatically. The heap, everything everything sticks around. So if we allocate a person, that person object will stay here on the heap forever until it gets deallocated. And can anybody tell me what the term is for an object that is on the heap and doesn't get released? There's a term for this. Yep, it's called a leak, a memory leak. So whenever you, like Firefox used to be notorious for its massive consumption of memory. It's gotten better over the years, but one of the things everybody always complained about was, oh, I launched Firefox and I've had it open for 20 hours and now I don't have any memory left on my computer. Well, that's because Firefox used to be very notoriously leaky. It used to leak a lot of memory, and the more you used it, the more it would leak memory, and it would never deallocate that memory. And then Chrome came around and beat the crap out of Firefox, and now there's no reason to use Firefox. I'm not opinionated. Anyway, so what we have here is a object that's going to stick around on the heap forever and until it's released. But like I said, every single language has its own way of dealing with this problem. Some languages are very simple. C and C++, for example, it's very simple. You have new. C, you have malloc and free. These are two functions. One creates dynamic memory, one releases dynamic memory. C++, we have new and delete. C# and Java and many other languages have new and then a garbage collector. A garbage collector is an automatic thing that automatically deallocates memory when it's no longer being used. Now, we're not working with any of these languages, we're working with Objective-C. A Objective-C, its memory management is a little bit more complicated. But it's kind of complicated in a good way. It takes the best from, or I'm not going to say the best, but it takes the concept of new and delete and kind of sort of combines it with the concept of a garbage collector, but not really a garbage collector. It's kind of this thing that exists kind of sort of in a place. And what it's called is reference counting. So Objective-C has ref counting. So it has new or alloc and ref counting. Now, ref counting is a combination of two method invocations that you can call on any object: retain and release. Retain tells the object to increment its reference count. Release does two things. Release will tell the object to decrement its reference count, and if the reference count reaches 0, to destroy that object. Every object in Objective-C has a reference count. So this person has a reference count. Let's say this person has a reference count of 1. That's because we just instantiated this person. So let's say we're inside of a function called, it returns a person pointer, and it's called create, and it instantiates a person. What happens here is the reference count of person gets set to 1. That means that if I were to release that person within this block, that person object would be erased from memory. But obviously I don't really want to do that here because this method is returning a person. So I want to go ahead and return the person with a reference count of 1 so that it doesn't get destroyed. The invoker of create will call release whenever that person is no longer used. So let's say I have a void bleh, and he creates a person by invoking create. Now this person object, called P, has a reference count of 1. If I were to do P release right here, what would happen is the reference count on this person would get decremented to 0, and the person would be erased from memory. But what if there we go. What if my bleh method, let's say I have another object called, let's say I have an object called people. So I'm going to add an object called people. And he has a reference count of 1. But what if in my bleh method, I want to tell people to add a person? Add person P. Now, I've instantiated the person. I've added the person to the people object. Then I'm going to release the person because bleh no longer needs a person. So it does P release. Now, let's pretend that the people object has a method called addPerson, and that addPerson adds that person to an internal collection inside of people. So we could say that a person is now owned by the people object. In this case, what happens when I call p.release? Hello. Hello.
Hello? Anyone?
Did my buzznet die, or is...
No?
Oh, there, Saturn says hi. But what happens when I invoke p.release? Person's gone. Right. That's undesirable behavior. Because my person reference, people now has a reference to person. So people now has a person pointer inside of him. And this person pointer points to this person object. And when I call p.release, this is decremented to 0, and the person gets deleted. Does anybody see the problem with what's going on here? We still have an object called people, and it still has a pointer to a person. Yep, that pointer has nowhere to point. Does anybody remember the terminology for this? There's a specific actual programming term that I love saying. Does anybody remember? If anybody was in my C++ class, I know I said it quite a few times. It makes me giggle every time I say it. Well, giggle on the inside. This person pointer is now said to be dangling. So it's a dangling pointer. It has nowhere to point. So Ray Lewis is exactly correct. This scenario is suboptimal because it results in a dangling pointer. What I want is the add person method on people to call p.retain. By retaining this pointer, we increment it to 2. Now the reference count is 2 as of this line right here. So this is the line we're currently looking at that just executed. Now our person reference count is 2 because the add person method of people retained that person object. Is everybody following along so far? So now what happens when we execute this line? It goes back to 1, exactly. But because it's at 1, it does not get deleted, and we no longer have a dangling pointer. So, the moral of the story is...
No dangling pointers.
Yeah, no dangling pointers, no memory leaks. And the way we accomplish that is following a simple set of rules. And if you follow this set of rules, you will never have memory problems. And actually, let me guys tell you a secret real fast. You're going to fail at following these rules. Inevitably, you're going to have a problem with memory at some point. That's with languages like Objective-C, that is the #1 cause of programs to crash, is dangling pointers or memory leaks. And so inevitably you will run into a situation where you forget to release or you forget to retain, and you will have a bug in your program. It's important to understand what's going on so you know how to fix it. And it's also important to understand what's going on so you're less likely to make that mistake, but like I said, you will inevitably make this mistake many, many, many times. So this should be probably the first thing, when your program crashes, the first thing to check is this, because it's the most likely cause of your program crashing. So the rules are, if an object needs, or if an object stores a pointer, retain. When an object no longer, stores a pointer. Release. Functions that don't store a pointer externally to the stack, so outside of stack, should always call release. So that's what the behavior we're seeing right here. People.addPerson stores a pointer in a collection in the people object. Because it stores a pointer inside of itself, that method should always call retain, because it's retaining that pointer to that object. However, this function itself, all it does is it creates a person, and then it's done with the person. So the function does a release. And the reason the function does a release is because the function itself does not store any pointer to that object external to itself. That pointer, that p variable, is local to that stack frame. And once the stack frame is gone, that memory, that variable is erased. So that's why the function calls release. But the method invocation, the addPerson invocation, should call retain because it adds an item to a collection inside the object. This also counts for objects that take in things through constructor parameters. So if I had an object that took in another object through a constructor parameter, that object should retain the object that was passed into the constructor, because that object is going to be storing a pointer to that object for the duration of that object's lifetime. When that object's lifetime is done, when it gets destroyed, it should release that pointer so that the other object may or may not be released. So anytime a method takes a pointer, you should retain, not necessarily. If I have an object, or if I have a function called something like void print name that takes in a person pointer called p, and all this function does is says print p indirect member access name and returns, is this code correct or is this code incorrect? Okay, we got one correct. Anybody else? By the way, the wager is about having to watch the first season of My Little Pony in a single day. So you guys willing to take that bet? Come on. So we got one correct. Those are some pretty high stakes. Well, come on, it's not fun if you're not betting something. We got another correct. Okay, I'm about to wrap this up. Okay, third correct, and you guys are all right. This method is correct, or this function is. The reason it's correct is the function never stores a pointer to that person object outside of itself. In fact, it's very difficult for a function to do that unless that function is a method inside of an object. So let's make something a little bit more complex. Let's talk about, what if a method is inside of an object and it sets so let's say I have a class here called thing, and that class thing has a private, whoa,
Holy moly.
that wasn't what I wanted to do. a private person pointer called owner, because the thing has an owner, and then it has a method called void set owner that takes in a pointer to a person, and let's just use P again. And the void set owner method says underscore owner equals P, then it returns. Is this method correct or incorrect? Anyone? So this is a field that is local to this class. Okay, so we got one incorrect, and the same wager stands. I suppose other people are thinking about it, hopefully, or they maybe just gave up. Got another incorrect.
People are saying incorrect.
Okay, we got two incorrects, and that's right. This method is incorrect because we store a pointer to something that's more persistent than the method itself. See, this P variable is not persistent, it's volatile. It's going to disappear the second the set owner stack frame disappears, so we don't need to retain or release this P. But we assign the value of P to a field, and a field is longer lived than the method. The field lives longer in memory than the method does, which means we have to retain owner or P. It doesn't matter which one we retain because they're the same object, but for the sake of clarity, I'm going to choose to retain on owner. But to do the same thing. By the way, I have no idea what programming language this is. It's like a mix between Objective-C and C# and Python. You're assigning a pointer address to owner. If it releases, you have a dangling pointer. Right. If I did not retain this object, then I could potentially have a dangling pointer. So remember, in the heap, we have a person object. And it has, let's say it has a reference count of 1 for right now. When it comes in, it has a reference count of 1. So that's all good. But then I do something special. This is the rule that I'm talking about. If our method assigns the address of the pointer to another pointer that is longer lived than the method, we have a problem, because this owner variable is going to be still pointing to this person long after this set owner stack frame is erased. Which means that if somebody else released this person, let's say whoever instantiated person, let's say a function called foo. So this is a function, and it releases after set owner is invoked. Foo releases the person that it passed into set owner, as it should. What's going to happen is the reference count is set to 1, but that's going to cause the reference count to be set to 0 and the person object to be destroyed. Now our owner variable, or local field, is now a dangling pointer because it's pointing to a location in memory that has been destroyed. However, because of the way we wrote this code, we did a retain. And what does the retain do? Well, all the retain does is it increments the reference count. So now our person has a reference count of 2. Now that the person has a reference count of 2, what happens when foo releases person? Well, now when foo releases person, the reference count is set back to 1. The reason it's set back to 1 is because there's that 2. Now it gets decremented. But because it's now at 1 after foo released person, it's still in memory and doesn't get destroyed. Which is what we want. Because until this object is destroyed, we want to retain a reference count to the owner field that we assigned it to. It's basically saying this object now owns this owner, which is kind of backwards because the owner is supposed to own the object. But bear with me. This object owns a reference to the owner. So how are you doing, Ray? Does Objective-C have scope? Yes, it has scope just like every other language. Ooh, Dialyc. We don't want to use Dialyc. The reason we don't want to use Dialyc is Dialyc will just go in, it will ignore the reference count, and it'll just destroy the object. How does thing bring person to 0 then? Through the destructor, which actually is, I believe it's called Dialyc. Is it called Dialyc? I forgot the name of the method. Why did I forget the name of the method? Okay, and we're back. Just some quick terminology issues with some of the ways that Objective-C is set up. Now, what we have here is, let me go ahead and make my canvas size a little bit bigger. Or a lot bigger. Whichever one it wants to do. I don't really care. So what we have is we also have something called the Dialyc message. Now the Dialyc message should never be called directly. Never invoke the Dialyc message directly, ever. The Dialyc message will be automatically invoked when the reference count of your object reaches 0 by invoking the proper amount of releases and retains to your object. Yes, the Dialyc does get called when the reference count is 0. Now, Dialyc is where you release the objects that your class owns. So a person was asking, when does owner get released? Well, owner gets released when the thing gets released. So what I'm going to do is, if owner does not equal nil, owner release. Now what that will do is that will bring the person's reference count down to 0 and destroy it. Okay, I'll give whoever comes up with the answer to this question, I'll give them an internet cookie.
I want a real cookie.
No, unfortunately I can only give out internet cookies.
Okay.
That's all we have a budget for.
Okay.
Can anybody tell me where the bug is in this class? There's a bug. It's a pretty nasty bug too. Can anybody see the bug? Finding bugs like these are incredibly important, and being able to identify them quickly. And Rowdy Bull got it right. If I set an owner to a person, and then I set an owner to another person, the first person will have a lopsided reference count, because the first person object never gets released. So to fix this code, what I need to do, again in my super...
It's magic.
Yeah, well, it's always magic. Magic of friendship.
Do magic, Nelson.
So to fix this bug, what I'm going to do is before I say owner equals P, I'm going to say if owner does not equal nil, then owner release. Otherwise, or in addition to, set owner to P, and then retain owner. So Rowdy Bull gets an internet cookie.
Yay!
Ray Lewis, is this making any more sense? Or is there... Yeah, retain will increment the reference count by 1. So plus 1. Release will decrement the reference count by 1. Keep in mind, though, I'm not retaining and releasing on the same object because I changed the object that it's pointing to right here on this line. What is the sign you use with primitives? We're not going to be covering that just now. We might take a look at that later. But so are there any more questions? Is it anything more? Is any aspect of this fuzzy for people? I mean, is there anything like kind of more specific that I might be able to drill down on? Because we've covered a few important cases. We've covered methods that create an object but don't hold on to them, so they release. We've talked about methods that do hold on to references, so we added retains. We talked about destructors on how when a class is deallocated, we want to release the objects that it points to. Does anybody have any more things that they want me to go over specifically?
Looks like everybody's good.
Alrighty. I mean, you know, we have pretty much all the time in the world here for people to ask questions and go over some of the concepts of what we're talking about. I mean, the concepts of what we're talking about is pretty language agnostic. The mechanism that we're using in Objective-C, there are similar mechanisms that are not built into C++ but are available in C++. And then you also have languages like C# and Java, which are garbage collected. But the difference between this and a garbage collected language isn't that much, other than the fact that we have to do this manually. A garbage collected language will do this. It won't do this process automatically. Garbage collectors typically work in a different way, but they perform the same operation, where they detect when objects are no longer being used and then they destroy them. Yeah, that's a good question. Did anybody struggle on any aspect of the homework? Because now would be a good time to go over that as well. Alright, I'm going to go ahead and pause the video real fast. And we're back. So, yeah, we didn't have any more questions. I hope that I went over some of the concepts that are really important for understanding how we retain and release our objects and under what circumstances we might want to send the retain and release message to one of our objects. And again, just to recap that, we do that so that our dynamic heap doesn't get filled up with unwanted objects. And it's very important because modern applications dynamically allocate lots and lots and lots and lots of objects. And when it dynamically allocates lots and lots of objects, and there are very complex relationships between those objects, it's very important to have a clear mental model about under which circumstances those objects will be available and under what circumstances those objects will be deallocated. So if you follow these rules that are right here, you will be good. You don't have to think about your memory management as an entire entity. You really, if you focus on these rules just in the context within the methods that you're working in, then everything will just take care of itself. And that's sort of the model of memory management that Apple has made available in the Objective-C language. So it's important to just keep these rules in mind. And hopefully I went over some stuff that made some of these rules make sense, because these rules aren't arbitrary. They come from a completely logical place. And I hope that just an alternate perspective on these sort of things, and just a reiteration of some of the things we went over last week, help people to understand why these rules exist and under which circumstances to apply them. So I think that's going to go ahead and wrap everything up. I hope people learn things and stuff. And to all the future people, we will see you next week. Bye.
Bye.